Get started. Last time we finished up chapter 18, which was nuclear chemistry, which was the last chapter on your exam, which is 1 week from today. Nuclear chemistry and electrochemistry, I think, is the two. So again, like I mentioned last time, we're not going to do chapter 19. So we're just going to go to 20, I think, here. And in this chapter here, we're going to talk about transition metals. And then we will get into really the main part of this chapter, which is coordination compounds, complex ions. We're just going to kind of go over some information about transition metals, which hopefully is probably review. But again, it's important because a majority of the metals within a coordination compound are transition metals. So understanding the properties of them are kind of important in terms of this. So let's get into some of the trends and properties of transition metals and some of the periodic trends which are important. For example, here, effective nuclear charge, which is Z effective. And if you're not familiar with sort of what effective nuclear charge is, it has to do with really electrons and specifically those sort of outer electrons because they are further away from the nucleus. They do not feel as strong of an attraction to the nucleus because of the process known as shielding. So take just a basic example, it doesn't have too many electrons going on there. Lithium, which is number 3 on the periodic table, has an electron configuration of 1s2, 2s1. This would be its valence electrons. These lower energy level guys are the core electrons. So what happens in this sort of situation when we look at sort of the electrons that are involved here, lithium, which has 3 protons, has basically a positive 3 sort of charge on the nucleus. And remember that the first number here is the principal quantum number, which is the energy level. So like on the first energy level, they got a couple of electrons, those core electrons hanging out at a energy level a little higher there on the second, which would be this guy, is where our valence electron is. Now, the idea here of effective nuclear charge is this. These kind of lower energy electrons, which are closer to the nucleus, these core electrons, they're pretty much right there near the nucleus. There's really kind of nothing in their way between them and the nucleus. And they do feel a much stronger positive attraction to the nucleus. So remember, opposites attract, right? So positive things and negative things are attracted to each other. And the strength of that attraction does increase with increased charge size. Now, when we look at our valence electron, which is on the second energy level, which is further away from the nucleus over here, this electron here is not feeling as strong of a positive attraction to the nucleus. And that is because of these lower energy electrons. They are doing what is known as shielding. And essentially what they're doing is shielding that outer electron from the full sort of brunt of positive charge from the nucleus. So instead of feeling a +3 charge like these lower energy electrons are in terms of attraction, this outside electron is actually feeling a much lower positive charge. That's what's known as effective nuclear charge, or Z effective. You could actually calculate it. It is the number of protons in the nucleus minus the number of electrons that are shielding, and in this case, that is 2. So effectively, that outside electron over here, the valence electron, is actually only feeling a +1 attraction to the nucleus rather than that +3 attraction. And that means that it is not going to be held as tightly as those kind of core electrons. And as you hopefully know, it is those outer electrons, those valence electrons that are involved in bonding, both types of bonding, ionic bonding, covalent bonding, and they are easily removed than the core electrons because of this. One of these factors here is effective nuclear charge. So if we take a look at this chart here, we can see sort of the trend. We got sodium, magnesium, aluminum. We're going across period 3 on the periodic table from left to right. And what we do see is the effective nuclear charge actually increases. And when you look at the periodic table, As you go up and to the right, the Z effective increases. And as you go down to the left, it decreases. This is also one of the factors as well that correlates to size, because as you go to the right on the periodic table, things get smaller as well. And that's also because even though there may be some more electrons involved, it actually has a greater positive charge and a greater effective nuclear charge. So what that means is even the outer electrons are going to feel a much stronger attraction to the nucleus than guys over here on the left-hand side of the periodic table, where they don't have as big of a positive charge happening in that case. What that does is just brings everybody closer to each other and in closer, and the result of that is size starts to shrink as you go up and to the right. And that's what we see here again. We do see size get smaller, and again, as you go up and to the right, the effective nuclear charge increases, and again, it's going to pull even those outer electrons in closer, resulting in a much smaller sort of overall size. Also, when you go down and to the left, you have a lot more electrons, so they do have to kind of space out, and they can't get pulled in as tightly. So as we are talking about transition metals, which again on the periodic table are pretty much right here. So these are our transition metals, and they do have some special properties that you may be aware of. Obviously, one of the ones you should be aware of, right, is they tend to be able to make a variable type of positive charge. And that's why when you name these guys, you typically use Roman numerals when you name these guys. There are three exceptions to that, and that's these three right here, that even though they are transition metals, they actually do have fixed charges, with zinc and cadmium being +1. I'm sorry, zinc and cadmium being +2, and hanging left there to silver being +1 in this case. By the way, down here, as you hopefully also know, if you follow the atomic numbers, those two rows actually go right about there on the periodic table. And sometimes those bottom row, which is the lanthanide and actinide series, is sometimes also referred to as intertransition metals, because technically speaking, they should slap themselves right there in the middle of the periodic table. When we talk about the periodic table and also electron configuration, which we'll talk about here in a second, and again to review, remember that transition metals are the d orbitals, is where, bless you, where those start. Remember the first couple of groups over here are the s orbitals, because they can hold 2 electrons. Like 3 through 8 is the p orbitals, because they could hold 6, 1, 2, 3, 4, 5, and 6. And this is our d, which could hold 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down here, our lanthanide and actinide series is the F block on the periodic table. F, because there's 7 orbitals, each can hold 2, is 14, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. There you go. You can count it off. As you may also know, you could also use the period number as the principal quantum numbers, and so forth as you go through here. One of the things you might be aware of, hopefully, is right around here when you get to the 4th period. That is 4s2 through here. Remember that Ds don't begin until the 3rd energy level, so that's actually 3D. So the 4s first, and then the 3D comes after it. That'll be 4D, 5D, and 6D coming down on that row. So obviously, transition metals show very great similarities when they're contained within the same sort of period, are in a group on the periodic table. They do form ionic compounds, and they do, as I mentioned, have the ability to make a wide variety of oxidation states. For example, Mn can make a ton of different oxidation states, from like +7 all the way down to like +2 and so forth. They are also usually the centerpiece for complex ions. So usually a complex ion, as we will see, will have a metal in the middle, and usually that metal is a transition metal, and they'll have a bunch of ligands that are attached, or molecules that are attached to it. And they can form these different types of complex ions depending on what ligands are attached, and really what ligands are attached can also give it different properties, even if they may have the same metal in the center. They have some different sort of ligands attached, they will perhaps have some different properties. By the way, ligands, as we'll talk a little bit more about as well in this chapter, again, are Lewis bases. A reminder that a Lewis base is something that can donate a pair of electrons. So when we talk about Lewis acids and bases, remember that a Lewis acid is something that can accept a pair of electrons, and things that typically can accept a pair of electrons are usually positively charged, like we typically will find our metal in the middle of this complex ion. So as we'll talk about, when we talk about complex ions, you can kind of think of it as almost a Lewis acid base interaction that's happening. We have the positively charged metal, which is very much electron deficient, and a good Lewis acid. And we have all these ligands, which are good Lewis bases that want to donate these electrons to it. And that is sort of how they come together to form these complex ions. And here's an example of such a situation. We have cobalt in the middle, and we have the NH3 here, which are the Lewis bases and the ligands that are attached here. Once again, NH3 is actually a pretty good Lewis base because if you draw it, it is a polar molecule, and it has those non-bonding electrons on the nitrogen that allows it to donate over to the metal and makes it a pretty good Lewis structure. And we do get this complex ion right here, where by the end of this chapter, you will name it properly. You know, the hexamine cobalt 3 ion would be the name of this guy, and you'll know how to name those before we are done with this chapter. Now, ionic compounds with transition metals, a lot of them do make solutions that have different colors. And again, the transition metal in that complex ion will typically absorb light at a different wavelength or a specific wavelength, which will give it a characteristic sort of color. A lot of compounds are paramagnetic. Paramagnetic means we got some unpaired electrons. Diamagnetic means that they kind of pair off with each other, those electrons. As we'll talk about at the end of this chapter, the number of unpaired electrons do give certain complex ions different characteristics as well, and different properties depending on how many unpaired electrons you got going on. So a reminder that when we do write electron configuration, and again, hopefully this should be a review, S orbitals could hold a maximum of 2 electrons. Any individual orbital could hold a maximum of 2 electrons. There's only one type of S orbital. It begins on the very first energy level, the n equals 1 level. P orbitals could hold a maximum of 6 electrons. There's 3 types of them, and they begin on the second energy level is when they first start to appear. D orbitals can hold 10 electrons, and they are 5 different types of those, and they don't begin again to the third energy level. And as far as you usually go, are F orbitals, are the F subshell, which is a grouping of 7 individual F orbitals. Each one could hold 2, which would give you 14 electrons maximum if you filled them all up. And that occurs on the 4th energy level. A reminder that there is, again, a specific order at which electrons go into the atom, and you write electron configuration, which is important for a little bit later on in this chapter, where you'll have to figure out how many electrons you're dealing with by writing the electron configuration. So if you remember sort of where each of these orbitals begin, you could create a chart really simply to figure out the electron configuration by just basically going 1s down to the right, 2p, 3d down to the right, 4f. And really at that point, all you have to do is just fill in the numbers with the letters underneath. And this will give you your proper electron configuration order. And 5f. And basically you always start at the top and then you just go back and basically zigzag. And a reminder where people always screw up, the 4s is actually lower in energy first, and they do get the electrons first, and then it goes to 3d, 4p, and back to 5s, and again so forth there through the d. So those s's always come before the d's because they are lower in energy. And there is a few exceptions to the normal sort of electron configuration as you might think about it. The two most people are responsible for are chromium and copper in the first row. And if we follow this chart, which we always start up here, if you wrote chromium, which is 24, and copper, which is 29, for chromium, you would do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 if you follow that chart. Once again, the exception happens here. There's actually been found experimentally to have a little bit more stability by having an extra electron in the D and one less in the S. And this part of the configuration through here is 18 electrons, which is where the argon comes from. Again, kind of noble gas configuration, sort of a shorthand. And again, we're going to promote an electron up in this situation, and we get 4s1, 3d5. Copper has a similar exception. It is one extra electron in the d orbital, one less electron in the s orbital. And they could very easily do that because those orbitals are super close in energy to begin with. So the 4s is hanging out pretty darn close to the 3d, and they're very, very close in energy to begin with. But the S is lower, so they do get those electrons first, and then we start to fill the d orbitals. By the way, again, a reminder that electrons, when there is a subshell and multiple orbitals, go in one at a time in the upwards position, and then they go back and pair off, right? So they just don't pair off right off the bat. Go one at a time and come back. The idea there is to maximize parallel spin where they're sending in the same direction. Now, if you look on the periodic table where chromium and copper is, and you go down and in, there is a ton of exceptions to normal electron configuration. Silver is an exception. PD is an exception. It actually has like no electrons up there in the S. They've all gone up to the D. So there's a lot of exceptions in those areas on the periodic table underneath chromium and copper. Now, one of the things that does happen when we talk about electron configuration is, especially with transition metals, once you actually start filling the d orbitals because they are higher in energy, there's actually a switch that occurs in terms of the energy. And once those electrons go into the d orbital, they actually end up being lower in energy, the d orbitals, than the s's, and the s actually becomes higher in energy. And that's really important for transition metals in terms of when they become ions. So when transition metals become ions and they lose electrons, they will always lose their s electrons first, and then they will dip into the d orbitals if necessary, if they need to lose more electrons. That is why transition metals, in terms of valence electrons, also equals the group number, but it equals the kind of 1 through 18 group number as you go through that part of it. And if you look at something like iron, 3, 4, 5, 6, 7, 8, iron has 8 valence electrons. It's got 2 in the s orbital, and it's got 6 in the d orbital. And technically, they're all valence electrons. Not that they would ever lose all those, but they do have them sort of available to them. So that's a kind of a strange thing that sort of happens with transition metals. They definitely will kind of lose those s electrons before the d electrons get lost. Any questions on that there? All right. So if we take a look at this, and that's what we see here, we take a look at Ti3 plus. Here's the electron configuration for Ti. The plus 3 means it has lost 3 electrons. So what's going to happen when it does lose electrons, once again, is going to lose the electrons out of the S first because they technically are higher in energy at this point, and then they will dip into the d orbital there, and they will take out the electron there, and we would end up with argon 3d1 in this particular case. Again, as I mentioned with iron, which is 26, is argon 4s2 3d6. This is its 8 valence electrons, technically speaking. So if you had iron 2, it would have 2 less electrons, and it would be those 2 that would go first, and you would end up with argon 3d6. If it went to iron 3, you would again take out those 2 electrons first from the S, and then you would go into the D, and you would end up with argon 3d5. So again, different than representative metals. When they lose electrons, they typically just take the electrons out of the last thing in the electron configuration, but here's transition metals, it's always the S's first. They also typically, unlike representative metals, do not reach noble gas configuration by losing electrons, like, say, potassium that loses 1 electron and ends up at the noble gas configuration. All right. So if we look at some of the oxidation states for our first row transition metals, you can see there's a wide variety of oxidation states that occur. And I could told you earlier, Mn, for example, has a ton of different oxidation states, +7, +6, +5, +4, +3, and +2. What we typically see is, in a lot of cases, very common oxidation states for our transition metals, +2s and +3s, occasional +4s. They kind of builds to the middle of the first row transition metals, and then kind of drops back down as we go towards the other side. Another really important property in terms of how electrons are either lost or gained, in this case lost, is ionization energy. Ionization energy is the energy, again, required to remove an electron from an atom in the gas phase. Electrons do come off one at a time, so they don't all just drop off at once. So if you had something like magnesium, the very first thing that would happen is magnesium would give up 1 electron. And this would be what is sometimes referred to as the first ionization energy, the energy required to remove that first electron from magnesium. The next thing that would happen is magnesium that's already lost an electron and it's positively charged would then dump off another electron. And the energy required to do that would be known as the second ionization energy, the energy required to remove the second one. And, just continue on in this fashion. Magnesium would then dump off 1 more electron, perhaps, and that would be our third ionization energy. As you may remember or know, it gets progressively harder to remove electrons one after the other. And that is because once you remove an electron, the overall size of the molecule electron cloud shrinks, and that moves everybody closer to the nucleus. So now they're held tighter. Another electron goes away, gets a little bit smaller. Everybody moves in closer to the nucleus, again, going to be held tighter. So as you go from the first ionization energy to the second, to the third, to the fourth, however many you got, it does tend to increase the amount of energy that's required to do so. The general trend for ionization energy is, when you look at the periodic table for first ionization energy, it increases as you go up and to the right, and it decreases as you go down to the left. The higher the ionization energy, the harder it is to remove an electron. The lower the ionization energy, the much easier it is to remove an electron. So for example, we take a look over here at magnesium, the one I did. It takes about 735 kilojoules of energy there to remove the first electron. When we go to the second electron, you can see it almost doubles there in terms of the energy required. It takes a lot more energy to try to rip that electron off as it's going to be held tighter. Now we go to the third electron, and now we're about, 5-ish times or 6 times in terms of the energy required to try to remove that third electron. Problem, though, is it's probably not going to happen because it's not very energy efficient to do so. If we look at the electron configuration for magnesium, 1s2, 2s2, 2p6, 3s2, magnesium has 2 valence electrons, and that takes you through here. This is not going to happen because that is now into the core electrons, which are beginning and have started closer to the nucleus and held a lot tighter, and now find themselves much, much closer as we start losing some of the other electrons. And energy-wise, is just not going to happen. That is why something like magnesium, as we know, doesn't get here. It just stops right there at the +2 charge and has a fixed +2 charge because of that. That's also why, for example, something like aluminum also has a +3 charge, because if you look at aluminum, first electron 580 to remove, gets harder for the second one, 1800, 2700. But now look what happens when you get into those core electrons. You're now looking at like 11,600 to try to remove it. Again, not energy efficient to do so, and doesn't happen under normal conditions. And again, that's why something like aluminum will kind of tap out there at the third electron and end up with a +3 charge. Here's a table similar to the one in your book, as some of the properties we've talked about. Again, electron configuration, atomic size, as you can see, starts to decrease as we go across the row there, transition metals. Ionization energy, again, gets larger as you go down from first to second to third, and overall gets larger as you go to the right on the periodic table. Common oxidation states, as I mentioned, very common 2s and 3s. We also see some density gets a little bit larger as you go to the right, and then starts to decrease as well. And again, there's our dots between the third ionization energy, third electron removal, and the first. And again, you can see much more energy as you keep trying to take those electrons off. In case you didn't like that graph, here's one with all of them on there, first, second, and third. Let's then talk about electron affinity. Electron affinity is basically the energy change that occurs when an atom gains electrons. So when we talk about ionization energy, we're really talking about cation formation, loss of electrons, some maybe becoming positively charged. When we talk about electron affinity, we're really talking about anion formation, when somebody becomes negatively charged. And it is the energy change that occurs when somebody gains an electron. So if you have a high electron affinity, that probably means you're pretty good at gaining electrons. And in general, the trend is it increases as you go up and to the right on the periodic table and decreases as you go down. It is not a perfect trend. For example, group 7 there, it increases as you go up, and then it kind of decreases a little bit there when you get to the top. So it's not a perfect trend, but it definitely, that is the general trend that occurs. Electron affinity should not be confused with the other thing that sounds similar, or people oftentimes confuse it with, which is electronegativity. And as you know, hopefully from bonding, electronegativity is the ability of an atom to bring electrons towards itself. So again, on the periodic table, increases as we go up and to the right, decreases as you go down, with fluorine being the most electronegative element you could have. And, they do all sort of kind of go together when you think about sort of the periodic trends, and you think about sort of what's happening and what happens on the periodic table. Um, when we look at the periodic table, we basically have effective nuclear charge increasing as you go this way, decreasing as you go this way. We have ionization energy increasing as you go this way, decreasing as you go this way. We got electron affinity increasing as you go this way, decreasing. We have electronegativity increasing as you go this way, decreasing as you go that way. And we got size, which is the only one that goes opposite, decreases as you go up and to the right, and increases as you go down. And what all these things together basically mean is when we go upper right of the periodic table, that is typically where we have our nonmetals located. And what we know about nonmetals is they typically like to hang on to their electrons, they like to collect electrons, and they don't like to give away their electrons. And these are typically why these guys typically like to gain electrons and are anions. As we kind of go the other side of the periodic table where we have metals, they are larger, they have low ionization energy, they have low electron affinity and low electronegativity, which basically means they're like, take my electrons, not a problem, and I'm not really looking to pick up any electrons, basically. And that's why these guys typically will make cations and sort of exchange it. That is also why we get the two different types of bonding that you're familiar with. Ionic bonding, which is between metals and nonmetals, because when those come together, they have very, very different periodic trends, where the metal wants to give away its electron and the nonmetal wants to accept it. So you get electrons that are transferred, no sharing of electrons in ionic compounds, and we end up with ions. And that's also why in covalent bonding or molecular compounds, where it's just a couple of nonmetals together, because they're both in the same area of the periodic table, neither one of those nonmetals wants to give away their electrons. They both want to accept electrons. So the best they could do is decide to share. And we get sharing of electrons that occur with covalent bonds and nonmetals together. And as you know, hopefully polar bonds, right, are unequal sharing of those electrons, and nonpolar bonds are equal sharing of those electrons. And again, these periodic trends is one of the things that really dominate why that happens. Any questions on some background there on transition metals, which hopefully most of that was review, I hope. This is what the first row transition metals look like, in case you ever want to know what they look like, I suppose. Um, these are things you don't have to worry about because you don't do general unknowns anymore, so you don't really care about the oxidation states of all these things. But you can see these different transition metals will have different colors in solution, yellow, blues, blue, greens, depending on the oxidation state that's there. Same thing with chromium as well, and Mn as well. All right. All right, then let's get into really sort of the heart of this chapter and really the main part of sort of what it's about, and that is coordination compounds. And coordination compounds are really, you can think of them as kind of like ionic compounds. There is basically two parts to them. There is a complex ion, and there is a counter ion. So both of those things together, the complex ion and the counter ion, is what makes up a coordination compound. Now, it is ultimately, really, like I said, really like an ionic compound. And as we will talk about, you could have a positive counter ion to balance out the negative complex ion, or vice versa. You could have a complex ion that's actually positive, and you could have a counter ion that is negative. Just like an ionic compound, and why you could kind of think of them as sort of an ionic compound is we typically always go with the positive guy first, be that either the counter ion or the complex ion, and then the negative guy second, just like we do in a traditional ionic compound. We also, typically speaking, in a counter ion, it usually will balance out to no charge on the counter ion, or I'm sorry, on the coordination compound. So in a coordination compound, they kind of balance each other out. And again, that is sort of the purpose of the counter ion, is to balance out the charge on that complex ion. So a complex ion is a metal in the middle, and again, uses a small, highly positive charge type of metal, +2, +3. A lot of transition metals make up the middle of complex ions. And then they have a lot of molecules or ions that surround it. And again, those are what are referred to as ligands. Again, those are our Lewis bases here. So again, these are our ligands, which again are Lewis bases. And once again, Lewis bases are basically things that can donate a pair of electrons. Water is a great Lewis base because, well, it's polar and it's got some electrons there that are non-bonding electrons. Things that make good ligands or Lewis bases are typically things that have electrons they could kind of donate. So being polar with some non-bonding electrons on an electronegative element is pretty good for it to be a ligand. Also, things that are negatively charged, as you hopefully know, right? The only way to become negatively charged is typically you've gained electrons, which means you have extra electrons to donate. So things with a negative charge are typically pretty good ligands as well. Again, as I mentioned before, you can think of this as like a Lewis base and the metal acting as like the Lewis acid, which because it is positively charged, is electron deficient and willing to accept those electrons in. Now, a ligand has a donor atom that is directly attached to the metal in the complex ion. And the number of atoms that are directly attached to the metal in a complex ion is what is known as the coordination number. So the coordination number is how many of these atoms are directly attached to the metal. So we take a look at that guy there on the previous slide. Directly attached here in this situation, this nitrogen is directly attached to the cobalt. This nitrogen is directly attached to the cobalt. The hydrogens are attached to the nitrogen, but not the metal. The chloride is directly attached. The chloride is directly attached. The nitrogen and the nitrogen here is directly attached. So in this complex ion, we have 6 atoms that are directly attached to the metal. And this guy would have a coordination number of 6. And the coordination number is not necessarily how many ligands are present. It is how many atoms are directly attached to that metal. Now, in some cases, the number of ligands attached and the coordination number will be the same, and they are the same when you have this type of ligand, which is sometimes referred to as being monodentate or unidentate. And basically what that means is in a monodentate ligand, the molecule will only attach through one atom. So something like water, when it attaches to a metal that is positively charged, will only attach through the oxygen. So you get like a 1-for-1 relationship there in terms of coordination number and ligands. Not all ligands are monodentate or unidentate. There are some ligands that can actually attach 2 atoms per molecule. Those are sometimes referred to as being bidentate. An example of that is ethylenediamine. This ethylenediamine is oftentimes abbreviated in complex ions as EN. So if you see EN in parentheses, it is referring to ethylenediamine. I'll take the old college try here on what it looks like. Looks something like this. And in this particular case, what's going to happen if you have a metal in that complex ion is each of these nitrogens will attach to the metal. So you basically get a 2-for-1 situation here. For every molecule of ethylenediamine, you get basically 2 attachment points. And what that does to the coordination number is it would double it. So if you had two of these, the coordination number would be 4. If you had one of them, the coordination number here would be 2, as again, you're getting 2 atoms attaching per one. That's probably a very common bidentate ligand. The other very common bidentate ligand is our good friend oxalate. Oxalate is also bidentate. If you draw up oxalate, it looks something like this. And oxalate actually has 2 single bonded oxygens, each with actually a negative charge on it, which again makes them pretty good ligands. And what's going to happen when a oxalate gets near one of those metal ions is both of those single bonded oxygens will bind to the metal. So once again, you're going to get kind of a 2-for-1 situation. So if you had something like this, we do this as a complex ion. A lot of times when people see a formula for a complex ion, they'll go, oh, yeah, the coordination number is this number down here. And in this case, it would not be. The coordination number in this case would actually be 4 because each of those are going to bind 2 places per molecule. So you basically would have 1 and 2 for one of those molecules, the other guy 1 and 2 for the other one, and that'll give you a coordination number of 4. Now, if it's monodentate, like you got this is going to actually be the coordination number because each of those water molecules will only bind in one place. So it's a 1-for-1 situation. The coordination number on this guy would be 6. But when you get into bidentate or polydentate ligands that can bind in multiple places per molecule, it is not always the little guy on the bottom. And again, that's a common error that people make. There are ones that combine in 3 or even more places. And those are sometimes referred to as being polydentate. And EDTA is a big molecule that can bind a metal in 6 different places per molecule. So it could really get around it and trap the molecule or the metal ion very, very much through all those individual bonding. Now, how many ligands do we expect? It does sort of depend, but there is sort of a general rule. So, for example, copper 1, silver, and gold 1 typically will join up with 2 or 4 in terms of the coordination number. When we get to things with kind of like a plus 2 charge, like we have in the middle, typically those guys will do 4 and 6s. And then when we get things with a really positive charge like plus 3, they're very electron deficient. They could get upwards of 6 things sort of attached to them. Except for gold. Gold 3 will typically do 4. So, usually the bigger the positive charge on the metal, the more electron deficient it is, the more availability it has to accept those electrons coming in. And you usually can then attach more ligands than maybe if it had a smaller one. There again is, as I mentioned, ethylendyl diamine. And again, you can see it will basically bond to the metal through both of those nitrogens. And again, you get a 2-for-1. This is EDTA over here. And again, as you can see here, it binds 1 molecule of EDTA. We'll do a 6 coordination on something. It will actually bind through all of those spots right there. And for 1 molecule of EDTA, it will basically grab up that metal. These are sometimes referred to as chelating agents. Sometimes you look on ingredients of certain things, you'll see something like EDTA listed, and a lot of times they're used to grab up metals and stuff like that and kind of get them out of there. And they're really good at it. Here's a table from your book and of some common ligands, again, unidentate or monodentate, water, ammonia, cyanide, nitrite, thiocyanates, OH minus, and any of the halogens. There's our 2 very common bidentate ligands, our oxalate and our ethylendyl diamine, which once again is very often abbreviated with just that EN. By the way, that abbreviation for En is used both in formulas and actually names as well. People don't like to write out that big old name a lot of times, so you will actually see that En abbreviation used both in the formula and also the name very commonly. This is basically like this is basically like En, but it's triamine, which means it has 1, 2, and 3 nitrogen atoms. So for every one of these through those nitrogens, you're going to get a 3-pack of binding happening here between this guy and the metal. And down there is our ethyl endyl diamine tetraacetate, and that's our EDTA. And as we saw earlier, again, it has those 6 different locations within the one molecule that basically can bind to a metal. All right, so let's take a look here. And one of the important things when we're talking about coordination compounds and complex ions is to be able to give the oxidation number of the metals within the complex ion. What we see here is actually 2 formulas, and these are 2 formulas for coordination compounds. And just some common sort of ways these coordination compounds are written. Typically, whatever is in the bracket, in most cases, is usually the complex ion part of the coordination compound. And usually whatever is kind of outside of the brackets, not inside the brackets, but outside the brackets, is typically your counter ion. So when you look at these formulas, again, what's in the bracket is our complex ion part. What's outside of it is typically our counter ion. So with that being said, why don't you take a moment here, and for the complex ion part in each of these, what is the oxidation state on the metal? So take a moment and see what you come up with. Speaking, in most cases, you'll kind of see a coordination compound written like this. There usually brackets, which is where the complex ion part comes into place. So right here within this bracket here is our complex ion part of our compound. The potassium in this case would be our counter ion in this case. Again, it's outside of it. So if we take a look at this here, our KAuOH4. So what we would want to start with here is pretty much everything other than the metal in the complex ion. I would start with whatever is attached to the metal in the complex ion. So OH is hydroxide as it disappears. And hydroxide, hopefully we remember, is -1 overall. There are 4 of them, which gives us like a -4 happening there for the hydroxide part. Potassium is group number 1, which means it is +1. And that means here to balance this out to 0, where we have no charge in this coordination compound, the gold would be going with an oxidation state of +3 in this case. First off, any questions on that there? We take a look at the other one here. Here is our brackets, which means actually here, this is our complex ion part. And it is the nitrate here that is our counter ion in this case. And once again, if we just kind of isolate what we got going on here, we got a little bit of this and a little bit of that. All right, so again, starting with what's attached to the chromium within our complex ion. That's NH3, which is, by the way, 0. It is not +1 because +1 is NH4 plus. This is NH3, which is ammonia, has no charge. Nitrate on the outside is -1, and there's 3 of them, which would give us a -3 there, a 0 there. Once again, to balance this out, the chromium in this case is rolling also, in this case, with a +3 oxidation state. Any questions on that there? Now, these are 2 good examples of what I was talking about earlier in terms of a coordination compound. When we look at the very first guy here on the left, and if we just look at the complex ion part by itself, so if we just took the complex ion part by itself there, which would be this part of it, What we know is, again, this is -1, and that's -4. The gold, as we figured out, is actually a +3. So +3 and -4 means that the complex ion part of this compound is actually an overall -1. So the complex ion part here actually has an overall -1 charge. And that is why when we look at my counter ion, which is potassium, group number 1, I just simply have one of those guys because +1 and -1 will equal 0, and I just need one potassium to balance out the charge. So that's the idea behind that. If we take a look on the other side here, and again, our other example with just the complex ion part, once again here, the ammonia is 0, and we figured out that the chromium in this case is +3. That means that overall here, my complex ion is actually positively charged in this case. It is a +3 positive charge. That is why when I look at nitrate, which is NO3 minus, I don't just have one of them, but I have three of them. And by having three of these guys as my counter ion, -1, -1, -1 is an overall -3 that will balance out the +3 charge here on my complex ions. So as I mentioned at the beginning here, you can have a complex ion that is negative and a counter ion that is positive, like we see in the first part here. You could also have a complex ion that is positive with a negative counter ion, like we see in the second guy there. But just like in an ionic compound, positive guy always goes first in the formula, negative guy goes second. And also when we talk about naming it, same deal, positive guy first, and then negative guy after that. Any questions on any of that there? So let's talk about naming. I know you probably thought maybe your naming days were done, but it's not. We have this one last wackiness to happen, I think. So as I mentioned before, when we name coordination compounds, or really if you're just naming complex ions as well, you will follow sort of the same rules for naming complex ions by themselves. Are coordination compounds that has a counter ion present. Once again, always positive guy first, the cation part, followed by the anion part. Within the complex ion part, the ligands that are attached to the metal in the complex ion, they are named in alphabetical order first, with the complex ion metal coming at the end. So there is in these guys a complex ion part of the name, and there's also a counter ion part of the name. So just like we saw on the previous slide where our complex ions in the brackets, when you're naming the thing in the brackets, which is the complex ion part, it is all the ligands coming first alphabetically, and the metal name comes at the end of that part of the name. Now, what I'm saying is the metal name may not be at the end of your actual name of the coordination compound, and it just needs to be the end of the complex ion part. Also, we will sometimes use prefixes if we have more than one of the same ligand attached. So when we do alphabetical order, we do not look at prefixes. So we look at the first letter of the ligand's name, regardless of whatever the prefix is. So if you have like triamine, we don't look at the T for tri, we look at the A for the amine as the ligand that's attached. So we ignore sort of the prefixes that are there. Some of the names of the negatively charged ligands will end with the letter O. Some neutral ligands are called by the name of the molecule, but a lot of them have some funky names. The exceptions is water, for example. Water is aqua. Some books will call it aqua with an A at the end. CO is carbonyl. NH3 is amine. When we do have, as I mentioned before, several of the same ligands within the complex ion, we do use prefixes like di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6. Now, if the ligand itself actually has one of those sort of prefixes in it, or a prefix in it, Again, that is 2, 3, 4, 5, and 6. We actually will use other sort of prefixes. So if the ligand itself does have a prefix in it, we will use bis for 2, tris for 3, tetrakis for 4 to indicate the number that is present. Now, what am I talking about? I'm talking about, for example, a ligand like En. That is name of that guy is ethyl endyl diamine. So because it has the di as part of its name, if you had two of these guys, you would not use di, ethyl endyl diamine. You would use bis because within this name, it has the prefix di in it, actually. So that is what they are referring to in this case. I will say that oxalate and the name that we use for oxalate when we call it a ligand, people tend to also use the bis, the tris, and stuff like that for those kind of polydentate type ones. The oxidation number of the metal is always written with a Roman numeral following the metal in the name. So we do use a Roman numeral to indicate the charge on the metal ion. And something that's unusual that we typically don't do in normal naming, for example, things like zinc or cadmium or silver, which have fixed positive charges, we typically do not use Roman numerals for those guys. But when you are naming these type of compounds, we actually do use Roman numerals. So for something like silver, we would put Roman numeral 1, even though it's a fixed charge. So we do include it. Also, something that's kind of unusual as well that you do run across occasionally is you will sometimes come across a metal that is neutral. It actually doesn't have a charge. And we do kind of include that in the name as well. We put a little parentheses and a 0 in the middle as well. So that's kind of a weird thing that sort of pops up with this as well. So we do use Roman numerals for everybody, regardless if it's kind of fixed charge or not. And we normally don't do that in normal naming, but here we do. That is a lot of rules. The next major rule is hidden down there, but this is the fun one. As we talked about a second ago, we can have a complex ion that is positive, and we can have a complex ion that is negative. And if your complex ion is positive, the good news is you just roll with the regular name of the metal. So if it's iron, you call it iron. If it's copper, you call it copper. If your complex ion is negative, you roll with kind of like an old school name for the metal that typically ends in 8. So if you had iron and it's in a negative complex ion, you would not call it iron in the name, you would call it ferrate. If you have copper that's in a negative ion, you would not call it copper, you would call it cuprate. Zincate is kind of had 8, and kind of the older school names, plumate, all those names you probably learned when they said, nah, we don't use those names, we use Roman numerals nowadays. For those guys that are negative, we kind of use those kind of older school names that end in 8 to represent it. So let's take a look at some of these names of ligands and stuff. As you can see there, water is aqua or aquo. Amine, that's methylamine, which is sort of the name in organic chemistry. Carbonyl. Our halogens are named very much like we do in organic chemistry: fluoro, chloral, bromo, iodo. Hydroxide is hydroxo. Cyanide is cyano. And here are some of those kind of metal names. And again, these are the names that we would use for the metal if your complex ion is negatively charged. So iron would be ferrate, cuprate, plumate, argentate, arurate, stannate for tin. And here's another table, some other sort of common ones that we come across. Again, bromo, chloral, cyano. Carbonate is carbonato. Oxalate is oxalato. Feel like you're ordering coffee, right? Carbonyl, amine. Again, this ethyl endyl diamine, like I said before, people just roll with the EN. And the ethyl endyl tetraacetic acid is that EDTA. So let's take a look at those two that we looked at to see sort of how we go about naming these guys. So let's take the first one here, which is KAuOH4. So the way that we name this is, again, always the positive guy first and then the negative guy. So in this particular case, we kind of already done all the work to figure out what everybody's charge is. That's obviously something that you would do to begin with, try to figure out oxidation states of everybody as you go through here. By the way, I know that the potassium here is my positive guy because it does come first in the formula, and this guy comes second, so it's negatively charged. So just by the location of how it's written in the formula, I do know that my complex ion in this case should be negative because it comes second here in the formula. Now, the good news about counter ions is we simply just use the name of it. So this would be, to begin with, just potassium like you would normally call it. So the counter ion pretty much is just named like its normal name. And also, just like in normal sort of nomenclature, it really doesn't matter how many you have of it. We do not use a prefix or anything like that. So we would still call that top one potassium oxide. If we happen to have two potassiums on the bottom guy there, it would still just be called potassium. So we don't usually incorporate any type of prefix on any type of counter ion name. Now, when we come here, what we see is we have 4 of the OH minuses. And again, if we roll through here and take a look at our chart, we can see that OH minus is hydroxo, and the prefix for 4 is tetra. And that is what we would kind of use. So we would come through here, and this would be tetrahydroxo. Now, what we also figured out when we were going through this is a negative ion for our complex ion, and that means that we would not call Au gold in this case. It's going to be the rate version of it, which is the older school. And again, we do need a Roman numeral here to indicate the charge on it, which would be 3. Now, earlier I mentioned that the metal name in the complex ion should come at the end of the complex ion name, and that is what we see here. We have the metal coming at the end, prefix before that, counter ion in this case before that. Any questions on that there? All right, so why don't you try the one next to it once you figure out what the name of that guy would be there. Okay, so let's take a look at, so again, we did some work on it obviously before, which you would probably want to do before you go about naming it. So earlier we saw the chromium was +3, this guy's 0, and this guy's -1. So the one thing that we figured out as well is this is our complex ion. It comes first in the formula, by the way, which tells us automatically it is positively charged. This was our counter ion. It comes second in the formula, which tells us it is negative. So once again here, we're just going to start with our ligands that are attached. We have NH3, which as you can see here is amine. We do have 6 of them, so the prefix for 6 is hexaamine. Here, because our complex ion is positively charged, we could actually just use the regular name there for our metal, which is chromium. So this would be hexaamine chromium, Roman numeral 3. And now we come basically to our counter ion in this case. And again, as I mentioned before, even though there are 3 of them in this case, as we talked about, we need 3 of them to balance out the charge. We just simply use the name of it, and this would be nitrate. Yeah. So this would be hexaamine chromium 3 nitrate. Once again, as I mentioned before, and this is an example of that as well, the metal part of the complex ion comes at the end of the complex ion part of the name. This entire thing here is the complex ion part of the name. It is not the last part of the overall name in this case. The counter ion is actually the last part of the name, but it is the last part of the complex ion name. First off, though, any questions on that name there? The coordination number for the one that we saw earlier, what would the coordination number on this one be? It would be 4 in this case, as OH is monodentate. So for every OH, you get one bonding end. So it would have a coordination number of 4. Coordination number for this guy would be 6. And again, that's because the nitrogen is the only thing that's going to attach. And there are 6 of them there attached directly to the metal in the complex ion. When we do coordination number, the counter ion is not included. Yes, because it is technically not attached directly to the metal in the complex ion. It's just hanging out there, balancing out the charge. What we're looking for coordination number is the thing that is how many atoms are directly attached. Lastly, to finish up on, if it was not a coordination compound, but just the complex ion part. So if you had this guy here without the counter ion and you need to name it, you would actually name it the exact same way as we did over there. This would still be hexaamine, chromium, Roman numeral 3. The only difference is instead of the counter ion, this is now just an ion. We just put ion at the end instead of whatever the name of the counter ion is. So that would be the hexaamine chromium 3 ion. The one up here would be the tetrahydroxo RU-rate 3 ion. And again, if you just need to name the complex ion by itself, there is no counter ion. You follow the same rules. You just put ion at the end of it and just follow the same sort of rules. Yeah. Any questions on that there? All right, we're laid up there for today, I think.